First, let me start by thanking the organizers for the invitation to speak at this conference. It's a pity not to all be together, but I definitely am glad that you decided to go ahead and have the meeting even in this virtual format. So my name is Jack Harris. I'm in the Department of Physics at Yale University, and today I'll be talking about projects in optomechanics. And I feel a little bit bad presenting these results at a conference called Non-Gauss, because we will be talking about definitely very Gaussian measurement results. But as I think you'll be able to see, this is work that's laying the foundation towards accessing non-Gaussian quantum states, non-Gaussian quantum physics. So what I'll be talking about is measuring individual phonons. Essentially, we have constructed what more or less amounts to a phonon counting detector, or a phonon heralding photon detector, that allows us to measure the phonon statistics in a nanogram scale superfluid cavity. So I'll start my talk by explaining why it is that superfluid helium is such a promising material for quantum optics, I would argue, and quantum acoustics. I'll give a motivation for studying optomechanical systems, though I think there are many different motivations. The one that I'll focus on is thinking of optomechanics as a way to approach macroscopic quantum phenomena. I'll talk about how single photon detectors can be converted to single phonon detectors, loosely speaking, and how the measurement back action of these detectors can serve as the kind of nonlinear resource that we need to access non-Gaussian states and non-Gaussian physics. I'll talk about first results from doing these kinds of measurements, and then talk about where we're headed a little bit longer term. I want to call your attention, first of all, to two posters that I think will be presented today. These are posters 14 and 16 by two graduate students working on this project, Yichi Wang and Lucy Yu. I definitely wanted to call out the contributions of Yogesh Patil, the postdoc who has led this project. And want to mention that this work is done in close collaboration with Jacob Reichel's group in Paris, and also in collaboration with Radim Philippe and others who provided us with theoretical support over the years. Okay, so as I mentioned, I was going to just give a brief overview of thinking about optomechanics in the context of macroscopic quantum phenomena. But that being the case, I then have to explain why macroscopic quantum phenomena might be of interest. And I think you could justify research in this area in three very broad ways. One is just pure intellectual curiosity. I mean, I think it is just astonishing that in Marcus Arndt's group, they can take something that looks like this and send it literally flying through meters of vacuum chamber, and then have it literally, just like, you know, the old thought experiments and real experiments, pass through a physical slit and then collect these molecules one by one on a screen and see the wave, matter wave interference associated with the quantum mechanics of this object's center of mass degree of freedom. And if the only thing that this field did was to keep pushing experiments like this to larger and larger objects, I would regard this as completely worthwhile endeavor. But there is also connection with the real world and practical devices. Mechanical sensors of different kinds have gotten so sophisticated and so robust that it's fair to ask whether accessing quantum effects in them can be used as a resource for new technologies, whether it's in astrophysical gravitational wave detection or more conventional chips-based MEMS sensors and the like. Lastly, it's possible that quantum mechanics of macroscopic objects differs in some important fundamental way from the quantum mechanics that we know to date. And while so far there's no evidence to suggest that this is the case, at least as far as I know, there are sort of reasonably well-founded hypotheses about how such differences might manifest themselves, whether it's in really nonlinear terms in the Schrodinger equation or non-trivial effects due to the gravitational field sourced by masses that are themselves in some kind of interesting quantum superposition. So these are three big overarching motivations for studying quantum mechanics on the macroscopic scale. The particular ways that my group and lots of other groups approach this is through what are called cavity optomechanical systems. And I appreciate Ulrich and Samuel's introductions to this topic. I would just briefly, in a nutshell, describe optomechanics as the following picture. We have a macroscopic object, which is usually an oscillator, whose quantum mechanical effects we are interested in measuring. But what it's much easier for us to do is to prepare a specific quantum state of the electromagnetic field, for example, from a laser, and have that state of the field interact unitarily with the macroscopic mechanical oscillator. And then also what we have very good technology for is measuring the quantum state or some facts about the quantum state of the electromagnetic field that has interacted with the macroscopic mechanical device. So in optomechanics, we really use our ability to control and measure light in order to indirectly control and measure the behavior of a massive harmonic oscillator. And so the requirement that this quantum state of light interact in some interesting way with the quantum state of the mechanical oscillator and then be accessible in the light that leaves this device hinges on unitary coupling between the electromagnetic field and the mechanical oscillator. And radiation pressure, or its various cousins like electrostriction, dipole forces, provides us with just that unitary interaction between the state of an electromagnetic field, typically a mode of a cavity, and the center of mass position of some macroscopic object. Now, radiation pressure is wonderful in that it provides us with an interaction between these two very different kinds of systems that's unitary, but of course it has the drawback that it's famously weak. You can go outside on a bright sunny day, interact with a lot of photons, but never feel the radiation pressure. The strength of this interaction is parameterized by the optomechanical coupling rate, which you can think of as the rate at which a photon in this cavity adds or subtracts a phonon from this macroscopic oscillator. And the basic Hamiltonian that governs this process is very familiar looking for quantum optics community. It's basically a three-wave interaction where the strength of the interaction is set by this optomechanical coupling, which you can think physically of as being the detuning in hertz of the cavity for every 0-point motion of the mechanical oscillator here. That's what sets the strength of the optomechanical coupling. And in building devices like this, there's some familiar figures of merit, dimensionless figures of merit that it's nice to keep track of, things like the cavity finesse, the corresponding quality factor of the mechanical oscillator, whether the oscillator is in the resolved sideband regime with respect to the cavity or not. We're typically working with oscillators whose frequencies are so low that even in a cryogenic system, the temperature of the thermal bath is relevant. So we want to know the mean phonon number of this mechanical oscillator. And then in terms of the strength of the coupling between the photons in the cavity and the mechanical oscillator, we'd like to know something about how strong the cooperativity, how strong the coupling between light and motion is with respect to the other relevant timescales, which are the decay rates of the cavity and the decay rates of the phonons in the mechanical oscillator. And very much an analogy with the atom cavity QED kind of parameter regimes, it would be awfully nice to be in this regime. It's known as the single quantum strong coupling regime, where the presence of a single, if you like, the presence of a single photon in this cavity would push the mechanical oscillator so much that the cavity would be detuned by more than a line width, and the next photon could not get into the cavity. This would be the analog of the usual strong coupling limit in atom cavity QED. But just in practice, for purely technological reasons, this has not been possible. So within this Hamiltonian here, pretty much all of the quantum effects that have been accessed just using this Hamiltonian fall in the weak coupling regime. There's maybe high cooperativity, but not single quantum nonlinearity. And the technical requirements are just all related to these parameters. We just don't have quite cold enough baths, quite high enough quality factor mechanical oscillators, not quite high enough finesse optical cavities, though they get close. Normally, so I've often given a quick introduction to explain why some kind of nonlinearity is required for accessing more interesting quantum states. And in Radeem's first talk of this session, I thought gave a really fantastic introduction to this concept of a hierarchy of quantum effects. I will just give a much more, much simpler, much more naive introduction to this basic concept. But just to illustrate the importance of some of the resources that we'll develop in the course of this talk. So if one is interested in studying the quantum effects in mechanical oscillators, it's very important to distinguish between what kinds of states one can prepare the oscillator in. For example, the ground state is a state in which you can prepare it and measure position, re-prepare it, remeasure position, re-prepare it, measure position over and over again until you have built up a histogram of results. You can also build up a comparable histogram of momentum measurements or of any linear combination of position and momentum. And although there are features associated with quantum mechanics in these measurement results, for example, the non-zero width, non-zero uncertainty in these distributions, these results can be thought of as arising from an underlying probability distribution that assigns a perfectly real, legal, joint probability to position and momentum. So if you like, this is a state in which measurements like this give you results that are perfectly consistent with a classical statistical mechanical interpretation. And frustratingly, the classical statistical mechanical interpretation that you would get just by taking this classical harmonic oscillator and coupling it weakly to a bath whose temperature simply happens to be h bar omega over 2. So even though we may think of the ground state or its cousins, the coherent states or the thermal states, as having, sorry. So even though we may think of the ground state and coherent state as having quantum features, for example, associated with these uncertainties, the more interesting structure of quantum mechanics, for example, the non-commutation, the sort of generic incompatibility of position and momentum as having pre-existing values, isn't evident in these kinds of measurements performed on this kind of state. A counterexample, an example of a state in which that kind of interesting quantum structure is evident in these types of measurements would be one phonon Fock state or one quantum Fock state, in which this corresponding story of preparing the state, measuring position, re-preparing the state, remeasuring position, building up a histogram, doing the same thing with momentum or any linear combination, results in perfectly reasonable looking outcomes, but outcomes that cannot be attributed to an underlying pre-existing probability of position and momentum, simply because the corresponding function would have to be negative, which means it's not a probability. And then Radeem gave a much more elegant and finer grained notion of this kind of hierarchy, and also pointed out, as I think is widely, would be widely agreed upon, that in addition to a hierarchy of single particle states, hierarchy of states for a single object, there's a corresponding, though not necessarily identical, hierarchy of quantumness in the states associated with multiple objects. So for example, whether or not an underlying probability distribution can be assigned to distinct objects that are well separated in space, for example. In any case, in keeping in mind this hierarchy of the more interesting and, from, for example, the point of view of quantum information, more powerful quantum states, that's sort of what's motivating the work that I'll be talking about today. It's also important to point out that in addition to the state that one is able to prepare, it's also crucial what kind of measurement one can bring to this state. So what I said before, I was sort of imagining a strong projective measurement of position and momentum, giving you real numbers, positioned measurements on each shot. And this is often a story that we tell in quantum mechanics classes and in basic descriptions of these kinds of effects. But in practice, in optomechanics, where we're trying to tell these stories with massive objects, certainly in the early generations of these devices, what one had is not a strong projective measurement of position or momentum, but rather a weak, continuous measurement of the reflected intensity or phase of a coherent state of light incident on the mechanical oscillator, which is a type of measurement which makes, even if states like this are prepared, tends to obscure these interesting structures. In a more recent generations of optomechanical experiments, including the ones I'll be talking about today, the sort of heterodyne or homodyne continuous measurement is replaced by single photon detectors that give a click type of photon counting detection, which makes it easier to access the kinds of physics associated with these states. And in some experiments, one can use a two-level system as an intermediary between the harmonic oscillator of interest and the photon detector, which can also be a powerful resource for studying this kind of physics. So this is all just sort of quickly to illuminate the concept that there's a hierarchy of quantum states. There's a hierarchy of the kinds of measurements that can reveal the physics underlying those states. Correspondingly, there's another question which I've implicitly introduced here, which is the notion of macroscopicness. And again, there is, I think, a way to make the notion of macroscopicness well-defined, albeit in a context-dependent way. I won't go into that in any detail, but for the purpose of this talk, to sort of appeal to one's intuition that larger or more massive objects might test some interesting corners of parameter space as regards quantum mechanics. Okay, back to optomechanics and this question of what kind of detection what kind of detectors one can bring to bear in these experiments. So the way that I would tell this story is that if one has a perfectly rigid optical cavity and sends in green photons, one gets out green photons. But if one of those mirrors is, say, a harmonic oscillator free to move back and forth, then photons that come in green can come out green, but they can also absorb a phonon from this oscillator and so come out blue. This is the blue sideband, or they can add a phonon to this mechanical oscillator and come out red. These are the red and blue sidebands. And of course, they have a classical analog, just as phase modulation sidebands. But if you have a detector here that's really going click with the arrival of every photon, then every photon that arrives here was either a blue one, a green one, or a red one. And in particular, the blue ones and red ones carry information about the quantum state of this mechanical oscillator. So every time there is a click from a blue photon at this detector, one has lowered this phonon number by exactly 1. And correspondingly, with a red photon, one has raised the phonon number by precisely 1. And this is what we mean by a phonon heralding event. And this is the basic idea that we'll use in our experiments. But again, the sort of weakness of this interaction presents us with a technical challenge, which is that only about 10 photons out of a billion are of this interesting blue or interesting red variety, and all the rest are of this uninteresting green variety. And since most single photon detectors don't themselves distinguish in a useful way between these photons, that's bad. Most of the clicks will just be boring, irrelevant green photons, and we have no idea which are which. So the idea, which has been around for some time in the traditional quantum optics community and has been applied very effectively to optomechanical systems by these groups here, is simply to put a filter here so that the filter is chosen to only pass, say, the red sidebands. And because of the mode structure imposed by this filter cavity, a click here has a back action on this mechanical oscillator that really corresponds to the adding of precisely 1 phonon to this mechanical system. So this, as I mentioned, this idea has been implemented by other groups in optomechanics. I think at the level of this cartoon in this picture, we're just copying the very nice demonstrations that have already been realized in this field. The thing that's a little bit different about our experiments is how we realize the optomechanical system and some of its parameters. Specifically, what we work with are Fabry-Perot cavities that are essentially conventional Fabry-Perot cavities, except they're realized through this incredibly beautiful technology developed in Jacob Reichel's group, where they take where they can take single mode optical fibers, laser machine a concave surface on them with ultra polished finish. Coating companies can deposit their high finesse mirrors on them. And if you point two of these fibers at each other, those curved surfaces and reflective surfaces guarantee you a high finesse, stable electromagnetic resonator, which is nice. It's very compact, very small volume, but really beautiful for operation inside of cryostats is the fact that this cavity mode is fairly well coupled to the traveling mode inside the fiber, which means that what you have once you take these fibers, and we have a nice way of aligning them inside of ferrules and epoxying them in place so that they're very robust, very rigid and solid. At that point, you have a chip, whatever you have glued these fibers to, with two fibers coming out that you can run out of your fridge, and there's no free space optics. There's no mode matching, or if you like, all the mode matching has already been done. And it's sort of as close to plug and play wiring for a cryogenic environment as one is likely to get for optical devices. Now, the empty cavity by itself is not an optomechanical system. It's just an empty cavity. So what we do for a mechanical degree of freedom is simply to immerse this cavity in a can of superfluid liquid helium. And it's the liquid helium that provides our mechanical degrees of freedom. So at this point, I want to give a little bit of an advertisement for liquid helium as a materials solution for quantum optics and quantum acoustics. This just checks most of the boxes one would want for such applications. The fact that helium has the largest band gap of any condensed material is nice in terms of low optical absorption, but much more important is that superfluid helium, because of its liquid nature and its superfluidity, typically has literally zero defects of any kind. Typically has zero non-helium atoms because a non-helium atom in a superfluid simply falls through the superfluid with no viscosity. And when it hits the wall of the chamber, which is maybe 10 millikelvin, everything except for helium freezes solid. So it's not uncommon to have sort of cubic centimeter size samples of liquid helium with zero non-helium atoms in them. In addition, the fact that it's a liquid means there's no structural defects. You can't have a crack in it. You can't have a missing helium atom. Electrostatics also mean you're not even going to have loose charges floating around in there. Anyway, it's an extremely low loss optical material. In terms of these same things contribute to a very low mechanical loss, including the strict absence of viscosity. In terms of keeping such a device cold, it's nice that liquid helium has relatively high thermal conductivity. This particular construction that we use of putting optical fibers inside of ferrules, and we have a nice kinematic arrangement for aligning them, means that there's literally no translation stages. There's no attocubes, there's no piezos of any kind in this device. And while we love attocubes and the Janssen precision engineering cryogenic translation stages, they work wonderfully, we also like not having to use them sometimes in some experiments. It keeps things nice and small. I won't go into this in the talk today, but liquid helium can play host to some very interesting hybrid quantum systems. And we have a proposal for trapping a 1D array of electron bubbles inside such a system and potentially making use of the ultra-coherent spins of those isolated electrons. Liquid helium has some interesting applications in dark matter searches. I won't talk about that today either. But in any case, it's just to say that liquid helium has not a lot of nice properties for these kinds of physics. For the purposes of today, what we're interested in is the coupling between light in the cavity and not a movable mirror, because that's not what we have here, but rather the acoustic mode is the standing wave of sound in the liquid helium. So I've just plotted here the optical intensity of one cavity optical mode and overlapped on top of it the time-varying density associated with a standing wave of sound, which is also confined by these mirrors. And one nice thing that happens in a cavity with this geometry, first of all, is that you get such things. you have acoustic standing waves inside the cavity, which are mechanical degrees of freedom. But a particularly nice thing is that because of this incredibly simple geometry of just having two mirrors confining your light, same mirrors confine your sound, it turns out that you get strictly zero optomechanical coupling between your cavity mode and every single acoustic mode except for one. And in the field of optomechanics, this is a persistent, annoying technical challenge, which is that you build a beautiful optical cavity, you build a beautiful mechanical structure, but any mechanical structure has lots of normal modes, and probably all of them detune the cavity to some extent. And so in practice, one is always sort of trying to use frequency discrimination to hone in on just one acoustic mode, and it works. There are a lot of ways of doing it, but it is kind of a persistent headache, I think, in the field. So in these kinds of devices, just the geometry of the device means that the only mode, the only acoustic mode that detunes the cavity is, there's only one of them, and it's the acoustic mode whose wavelength is exactly half of the optical wavelength. And you can think of this as sort of a phase matching condition in a Bruin scattering picture. I like to think of it as just an overlap integral. If I look at the optical intensity as this red curve and the change in density, which is this blue curve, the fact that I just have standing waves between mirrors means that all of these functions are orthogonal, except in this one case here, which gives me the nice optomechanical coupling. So again, in most quantum optic systems, it's nice, or at least it simplifies things, to have a strictly single mode coupling, which is just realized naturally here by the geometry of the device. So this is a photograph of what the devices actually look like. This is a pair of glass ferrules, a glass ferrule with an optical fiber poking through. Copy down here, the cavity is formed in the gap between them. It's straightforward to build a bunch of these devices. Again, there's no translation stages, there's no alignment once the structure is epoxied in place, so we build a few of them. Just goes inside of a can. The can has no electrical connections. There's just one fill line to bring the liquid helium into the can, and of course an optical fiber for each cavity. So it just bolts to a dilution refrigerator, and that's it. All this complication is the dilution refrigerator. A conventional dilution refrigerator would easily be able to house 100, maybe 1,000 of these devices. And as I'll mention at the very end of my talk, we think we have a nice way to add a little bit of complication, but to be able to make these devices indistinguishable from the point of view of quantum emitters. I'll say more about that later, but the bulk of my talk will just be about individual devices. So the setup in very simplified form looks like this. We have two lasers, one that's tuned up to drive the optical cavity close to the red sideband, and one laser that's tuned up to drive the cavity close to the blue sideband. That light gets directed into the superfluid filled cavity. Any light, including just the elastically scattered unshifted light, but also the interesting sideband photons, come out through a circulator. They pass through two high finesse filter cavities that are tuned up to pass only the motional sidebands. Those motional sidebands get sent to a pair of superconducting nanowire single photon detectors that are back inside the cryostat. And real data looks something like this. We go through every 100 milliseconds, the cycle of locking up all of these cavities, then 100 milliseconds of just letting them run freely, during which we actually count photons. And while the cavities are just tuned up and the photon detectors are on, we get clicks over about a period of 100 milliseconds. And the individual clicks themselves, so this is the analog voltage trace coming out of the SPD. And these are very sharp, so we can resolve the time of any given photon to less than a nanosecond. And again, the arrival of every, or not quite every, but the arrival of a sideband photon unambiguously heralds the addition or subtraction of exactly one phonon from this acoustic mode here. So what we can do is we can take data like this, record the average rate of photon counts, each of which is somehow associated to the phonons in the acoustic mode, as we tune the frequency of this laser back and forth. And this is the raw data shown here. This is the rate of these sideband photons as the drive laser is swept over. And I should mention that the acoustic mode that we couple to has a resonant frequency of 315 megahertz. And we've done a lot of characterization. We sort of know what's going on here. There's a background from dark counts, from leakage of light through the filter cavities and such. There are Brillouin photons that are produced by the optical fibers thermal fluctuation. This is a well-known effect in optical fibers. We've characterized this pretty thoroughly. But this narrow feature here at exactly the resonant frequency of the superfluid acoustic mode represents the sideband photons that I've been talking about all along. And if we repeat the same process by putting the drive laser over on the red side, we take very similar looking data, very similar backgrounds, very similar effects from the optical fibers, and a motional sideband on the red side, which is of a different height. And this difference here is what's known as the quantum sideband asymmetry. I'll show you sort of more evidence for that interpretation in a minute, but that's what it is. And in the rest of the talk, all this background, we're going to just regard as background. We've verified that it's, has very clean statistics. And in all the data that I'll show you, we have subtracted whatever would be appropriate for, Poisson distributed background, and focused on just the contribution associated with the motional sideband. So what we can do in that spirit is some of the following here. We can take data like this as we vary the temperature of the system and just track the heights of these peaks here. And that's shown here as the mixing chamber temperatures increased up to about 200 millikelvin. And what you can see is that the rate of sideband production is pretty closely tracking the temperature of the system, which indicates that the acoustic mode is in good thermal equilibrium with the fridge, at least down well below 50 millikelvin. And you can also see this persistent difference between the height of the blue sideband and the height of the red sideband, which is one of the things that gives us confidence in assigning this interpretation to this asymmetry. And based on that confidence, we use this as a calibration for all the effects that I'll be talking about later. Now, this is data taken with very low laser power going into the cavity. If you crank up the laser power up into the few microwatt range, we begin to see heating. So this shows these signals, sideband signals, as a function of the drive laser power, where I've divided out the drive laser power. So if everything was incredibly simple, perfectly simple, these would just be completely flat. But we see a couple things happening. One is that we see an overall trend of more counts. This we attribute just to heating of the device. So as we crank up the laser power, the device is getting hotter. We have a very simple thermal model for the transport of heat out of the device, and that model gives these dashed lines here. Based on the size of the sideband asymmetry, we calibrate the optomechanical coupling rate, and from that we can calculate just the well-known classical optical damping, laser cooling, dynamical back action effects, which are different when you take the blue data with a laser detuned to the blue, which gives you some anti-damping, and the red data, which is taken with a laser detuned to the red, which gives you some damping. So the contribution of this laser cooling or damping or anti-damping is the shaded region, and the combination of the quantum sideband asymmetry, which is this gap here, the heating, which is this dashed line, and then the dynamical back action fits the data pretty nicely. So this gives us confidence that we understand sort of what we're dealing with. It shows all the well-known phenomena of optomechanical devices. But this is all phenomena that you could access with a heterodyne measurement of the motional sidebands. So what we're interested in is the fact that our record contains much more information than just the mean rate of photon arrival. It contains the information about every single photon's arrival time. And so to start to take advantage of that, we look at the G2. We take all the delays between all the photon counts and make a histogram out of them and plot those up. Now, what we have access to, as I mentioned at the very beginning of my talk, is the photon arrival times. And if you calculate a G2, and in a minute we'll look at the higher order correlation functions. But if you calculate any correlation function based on the photons, which is what we have access to, and you want to interpret those in terms of the phonons in the acoustic mode, then the interpretation is a little bit different depending on whether you have driven the cavity on the red side band, in which case the optomechanical interaction is essentially a beam splinter interaction, and any normally ordered correlation function that you extract from your photon counting data corresponds to the same normally ordered correlation function for the phonons. Whereas if you have driven the cavity on the blue side, then the optomechanical interaction is a two-mode squeezing one. And when the photon counter gives you normally ordered photon correlations, and you want to interpret that in terms of the phonon operators, that interpretation will be in terms of the anti-normally ordered phonon operators, which we call H instead of the G. So just keeping that in mind, this is the corresponding data. This is the inferred phonon two-point correlation for when the system is driven on the red sideband. And this is the anti-normally ordered phonon correlation function that's acquired from data with the laser driving the system on the blue sideband. And the fit here is to the expected form for a single mode thermal state, and it's just shown in a log scale in the inset. And though this data looks very different, there's actually no difference in the predicted form of these correlation functions. The apparent difference is just due to the fact that when we drive the system on the red side, it is optically damped, and so the decay is faster. And when we drive the system on the blue side, it's a little bit anti-damped, and so the decay is slower. But the functional form is the same. With this kind of record, though, we don't have to stop at two-point correlation functions. We could look at three-point correlation functions. So we could look at every pair of delays and build a histogram out of delay pairs. That's necessarily a two-dimensional array where you have the time from the first click to the second click on this axis, and then the time from the second click to the third click on this axis. Again, the points here are the data, either driving the system on the red side or the blue side. The fit is to just what you would calculate from a thermal state. And since it's a little hard to see in these kinds of 3D plots, I've also just shown you the residual to show that the fit is quite good. We can go to 4-point correlations, looking at histograms of 3 delays. So for any 4 counts, you can look at the 3 delays between them and build up just a histogram of all such 3 delays. That's necessarily a 3-dimensional data cube, which is hard for me to show you. So I'll just show you one slice of that cube, one face of the cube, if you like. We have the entire cube, and the fit is to the entire cube, but I'm just plotting here one face of that, and that's shown here again with the theoretical prediction for a thermal state. So the takeaway from all of this is that the acoustic mode really is in a Gaussian state. It's really in a thermal state. We aren't just measuring the variance and assuming that it's in a Gaussian state, measuring the variance and the third cumulant and the fourth cumulant, and they're all consistent with what you'd expect from a thermal state of that acoustic mode. Even to the point that we can see that the fitted value of the 4-point correlation function at the origin is the expected 24. For the 3-point correlation function, it's very close to the expected value of 6. And for the 2-point correlation function, it's very close to the expected value of 2. Okay, so this is a very thorough characterization of the thermal state of the acoustic mode. We can do a bit more, though. We can take that enormous data record and then do some post-selecting and only look at data immediately after one phonon has been added or subtracted, or 2 or 3. I think that's as far as we can go. And what this is showing is the mean count rate immediately after the detection of one phonon. So if you have a thermal state and you've just gotten a click, you can take a sort of Bayesian point of view and say, well, that probably means that the thermal bath caused your energy to fluctuate high, and so the chances of seeing an extra bit of energy in this oscillator immediately afterwards is relatively high, and indeed that's this factor of 2 here. Again, from a Bayesian point, if you've just got 2 clicks, chances are that didn't just happen randomly, that happened because the bath actually caused your energy to fluctuate up. And so the chance of getting a third click, having just gotten 2, is correspondingly higher. And the same thing if you've just gotten 3 clicks. So that's all shown here along with the fits to theory. We can look a little bit further. We can say, suppose you just got a click, either adding or subtracting a phonon. Now look at the subsequent data record and calculate the 2-point correlation function, the G2, given that you just had that click. And that's data that's shown here. Again, fit to the theory for a thermal state, and it's in good agreement across all these different measures. So that is all looking at the acoustic mode just in equilibrium with the bath. If you like, it's a little bit perturbed from equilibrium by the driving laser, but that's pretty easy to understand. That perturbation is pretty weak. It just changes the acoustic mode's damping rate, if you like. And on post-selection, you can see the system not being in equilibrium, but it's as close to equilibrium as we can get in these kinds of measurements. So in order to begin to go a little bit further, what we've started to do is to look at what happens when you take the acoustic mode and apply a linear drive to it. So we do that by leaving our usual detection laser on. So we have one laser, in this case, maybe detuned to the red by 1 motional sideband, such that any motion in the cavity puts a photon resonant with the cavity that then comes out through our filters and gets counted on our photon counter in just the same way I've been talking about all along. But what we do is we add 2 other lasers that are not particularly resonant either with the cavity itself or with the filter cavities, but whose job is to produce a beat note, an intensity beat note in the cavity at a frequency close to the resonant frequency of the acoustic mode, such that it constitutes a linear drive of the acoustic mode. And if you do that, you would expect that the acoustic mode would be driven to a coherent state, ideally, whose mean phonon number would be something like the product of these 2 laser powers. And this is a measurement now of the photon counts produced by sidebands of this detection laser, counted on our photons, as a function of this drive frequency. So this is just the classic example of applying a drive, sweeping its frequency across the resonance of the acoustic oscillator, and measuring the oscillator's motion. But here we're not measuring its position, we're measuring individual sideband photons. And so here's the resonance line shape of the superfluid acoustic mode as the drive is cranked up higher and higher. And you can fit these to Lorentzians, you can extract their height, and indeed the sideband count rate, just as raw data, counts per second, is proportional to the drive power as expected. Based on all the characterizations that we've done, we can convert these photon count rates to a mean phonon occupancy of the acoustic mode, and that's just this same axis, just recalibrated in terms of mean phonon occupancy. So what you can see from this is that the line shape looks constant. We're not seeing a duffing oscillator. We're seeing that the height of that line shape scales as expected with drive, at least up to 20, 30, 40,000 phonons. So that tells us that the acoustic mode is nice and linear, that the detection scheme, that all the sort of optomechanics that's going on inside the cavity is all within a nicely linear regime, which is useful depending on what you want to do with these linearly driven acoustic modes. But what this doesn't tell us is how much noise we might be adding to the acoustic mode. So we know from our previous measurements that the acoustic mode equilibrates to a mean temperature of about 1 phonon. So in the sort of Wigner function picture, I think that's actually on the next slide, it'd be reasonable to ask, does the Wigner function of our thermal state, and it's almost a ground state, but it has some thermal fluctuations in it, when we apply this drive, does it just get displaced? Are we applying a pure displacement operator, or is our drive noisy, adding some entropy to the state of the acoustic mode? In order to answer that question, we look at the 2 phonon statistics. So specifically what we do is we apply the drive, we displace the system, certainly. We'd like to know whether, in addition to displacing it, we also smear out the Wigner function. And to answer that, what we do is we look at the record of sideband photons and calculate their G2. And that's shown here as a function of different amounts of displacement. So when the system is not displaced at all, when there's no linear drive, We're just looking at a thermal state. That's the palest data here. And then as we begin to displace the state more and more and more, the G2 gets closer and closer to being flat. I guess in this case, it's not actually 1. So I think I should check with the students if they're on the line, but if they are, maybe this represents some backgrounds, something that gets normalized out, or maybe this is really just not strictly the G2, but just a unnormalized correlation. In any case, this is certainly qualitatively what one would expect as the displacement gets larger than the sort of width of the noise ellipse in phase space. One would expect it to look qualitatively like a coherent state with a flat G2. Here's that a little bit more quantified. So we fit each of these curves to the expected form and extract out the value at 0 delay. And as a function of, this number is basically the number of phonons in the displacement. So this is sort of the number of coherent phonons, if you like. This is the size of the displacement normalized to phonon number. When the displacement is much less than 1 phonon, so when it's essentially an undriven, the G2 at 0 is basically 2. And as it's displaced more and more, it gradually transitions over to what you would associate with a coherent state. And that transition is shown here along with the fit. Here's the same data just shown with 1 subtracted off and plotted on a log scale. And in data like this, it's a little hard to see from here. The data gets much cleaner as we go to higher and higher amplitude displaced states because there are just so many more scattered photons. So the statistics gets much better. But of course, at some point, we bump into some kind of systematics with fluctuating laser powers or things like that. And so out here, mean phonon numbers on the order of 10 to the 4 is where just sort of other artifacts prevent us from doing a proper fit and really seeing what's going on in the 2 photon correlation data. So that's why it sort of peters out here. But the conclusion from this is that the drive that we apply doesn't add any entropy to the acoustic mode, at least for mean phonon numbers out to about 10,000. And just as sort of an amusing comparison, what that means is that the acoustic mode has the mean phonon number as though it was at room temperature, but it has the purity of a state that's at about 20 millikelvin. So that's sort of all the results that I wanted to tell you about. In the next few minutes, certainly less than 5 minutes, I'll just tell you about next steps where we see this going. We're in the process of building a second generation of these devices. In the present generation, one limitation that I didn't mention much is that the acoustic Q is rather modest. It's about 10 to the 5. And that is limited not by any problems with the superfluid helium. Helium really is truly wonderful, but it's limited by the fact that the sound waves, as they bounce back and forth inside this cavity, can eventually overcome the acoustic impedance mismatch and propagate into the glass. There's really nothing preventing that right now. So we're building 2 new kinds of devices, one we have in the lab already, and this is just essentially the same device, but now with a double stack of DBRs in the coating layer. One stack that's high finesse for the optical mode, as of course we want, but then a second set of layers that is designed to be a distributed Bragg reflector for the sound waves. And so will give us a high finesse acoustic cavity in addition to the high finesse optical cavity. And we haven't cooled it down yet, but the finite element simulations predict that we get another 2 orders of magnitude in the quality factor, and another 2 orders of magnitude, 1 or 2 orders of magnitude just from working with a longer cavity. So that means sort of 3 or 4 orders of magnitude improvement in the acoustic line width. The other approach that we're taking is to build a ring cavity out of these fibers now. This is a project we're collaborating on with Jacob Reichel, where the idea here is that, we should have thought of this a long time ago, is that sound has an extremely low speed of propagation in liquid helium, which means it's quite easy to confine it by total internal reflection. In fact, the Fabry-Perot geometry is like the only geometry that doesn't do this. So simply by building a standard triangle cavity, The acoustic modes will be confined by total internal reflection. And we expect very high finesse, very high acoustic finesse there as well. So either of these approaches should give us end up with a phonon lifetime on the order of 1 second, as opposed to a fraction of a millisecond in the present devices, which will be a big improvement. The other thing that we'd like to do is to take further advantage of just this incredibly simple geometry and add one more bit of functionality to the device, which is that each device would have its own shear piezo, which would allow some fine tuning of each cavity length. And once you do that, if you are then able to tune each cavity, not so that they're necessarily all this exact same length, but so that they're all resonant with a single laser, and drive them in parallel and recollect the light. This is obviously a very simplified schematic, but recollect the light and send it to a single photon detector. Then this heralding process, the detection of a single sideband photon here, wouldn't herald the production of a Fock state in a single cavity, but the existence of a single excitation across this entire array. This would herald the production of a W state across these devices, which has a lot of utility. Of particular interest is that this setup is all realized in telecom optical fibers. It's all realized with 1550 nanometer light. And each one of those excitations that's heralded in here, at least with the new devices, would survive for on order of a second. So this is promising for kind of quantum communications protocols. This would provide a mean for distributing entanglement over telecom photons, over fiber networks. These devices don't have to be in the same dilution refrigerator. They can be, we think, linked up by kilometers of room temperature optical fibers, with each device providing a long-lived quantum memory. So these are sort of the two things that we're pushing on at present. That's the end of my talk. So in conclusion, what I told you about is, along with other groups, we are using the counting of sideband photons as a nonlinear resource in optomechanics. We're doing this in superfluid devices, which have a number of advantages. This true single mode coupling between photons and phonons. They're really efficient at being cooled by dilution refrigerators. They're at the nanogram scale, which is sort of not the smallest, not the largest, but interesting scale to work on. We think we have a clear path to our next generation of devices in which the phonon lifetime can be pushed up by 3 or 4 orders of magnitude, in which we can make truly indistinguishable devices, and not just like 2 devices by getting lucky with the fabrication, but like we have a generic way of tuning up these devices into an arbitrarily large number of indistinguishable devices. We have one of the devices that's presently in the lab sort of has scaled up just all the dimensions so that it's a microgram sized acoustic oscillator. The actual data that I showed you today, we sort of confirmed the Gaussianity of thermal states, specifically thermal states with a mean phonon number of about 1 out to the 4th cumulant. We also looked at post-selected statistics for phonon added and subtracted states. And we showed that this purity is maintained even with a coherent drive up to a mean phonon number of about 10,000. So in the near future, the things that we would like to do is to use these technical improvements to test some of the inequalities that Radim talked about in the quantum hierarchy. And students from my group will be presenting posters on this. And we'd also like to use these technological improvements to as a route for really practical entanglement distribution over fiber networks. We'd like to use these high amplitude coherent states to test some interesting predictions about quantum gravity and quantum spacetime effects. We're collaborating with a big group at Lawrence Berkeley Laboratory on using superfluid phonons as a detector for astrophysical dark matter in a sort of interesting corner of dark matter searches. And we have a proposal paper that should be coming out soon on the prospects, which seem quite good, of using these devices to trap individual electron bubbles in the device's standing waves, and using that device to read out the spin of the electron bubble, which has never been done to date, but is predicted to have incredibly long coherence times and have lots of potential applications. This work, which is kind of what I show here, is going going on in parallel with two other projects in my group. The other is to look at really qualitatively unexplored regimes of optomechanics using magnetically levitated drops of superfluid helium. We've made some progress in levitating millimeter-sized drops of helium, measuring their acoustic modes. We would like to push this into the quantum regime, and in particular, study the quantum mechanics of the free rotation of a truly isotropic object. We have another project looking at topological dynamics and exceptional points in non-Hermitian oscillator systems, which is coming along nicely. And with that, I will just thank the students and postdocs in my group, in particular Ichi and Lucy, who are presenting posters today, Sean Fraser, and especially Yogesh Patil, the postdoc who has led this project. Thanks to our theory collaborators. Thanks very much to Jacob Reichel for working with us on producing these devices, and thanks very much for your attention.